In this video, we're going to learn how to derive the formula for the area of a circle. We've learned how to inscribe certain polygons in a circle. As we inscribe polygons with more and more sides, it creates a better estimation of the area of a circle. I'm going to use a program called Geometer Sketchpad to demonstrate this. So I'm first going to inscribe a square inside this circle. So I have a circle, and I'm going to make two diameters that are perpendicular to each other. Change that to solid. Alright, so here's our first diameter. And hide that line. Now I'm going to create a perpendicular bisector to this diameter. I'm going to highlight the line and highlight the center, which is going to be the midpoint of that diameter. And I'm going to tell the computer to construct a perpendicular line. Now I'm just going to trace it with the line tool, the line segment tool. And then I'm going to hide that line. Now I've got the two diameters perpendicular to each other, and when I connect those end points of the diameters, remember that makes a square inscribed in a circle. Now that square could be used to estimate the area of the circle. Now it's not real close to the area. There's some space missing here and here, and it's between the arc and the edge of the square. But we can make another polygon that's even closer and a better approximation. Now you can also, this is called an inscribed square. You could also do a circumscribed square. So to do a circumscribed square, I'm going to construct a tangent to the circle. So I'm going to construct a perpendicular line to this radius. Then I'm going to construct a perpendicular line to this one at that intersection point. I'm going to do that all the way around the circle. Construct perpendicular line, construct perpendicular line. Again, I'm going to outline the square using the segment tool. And each one of these lines is, line segments is tangent to the circle. Now I can hide each one of these. So display, hide. And now we have a square circumscribed about the circle. And that could also be used as an approximation. So the area of the circle is less than the circumscribed square, but more than the inscribed square. Okay, so now I'm going to bisect each one of these segments. So I'm going to highlight each of the segments inside, and I'm going to construct the midpoints. Then I'm going to construct the bisector. So I'm going to connect each one of those. So construct these lines and highlight that, don't need that one, and construct the line. Now I have bisected all four sides of the square, and now I can connect these points. And remember that when you bisect the chord of a circle, you also bisect the arc. So where this line intersects is cut the arc into two congruent parts. And so now I'm going to connect all of those points of intersection, and we have created an inscribed octagon. And that octagon is now going to be a better approximation than the square. So I'm going to hide the square. And so now we've got an octagon inscribed in the circle. And now there's less space there, so that would be a better approximation. We could find the area of each one of these triangles using the formula area equals 1/2 base times height. I'd actually have to find the height of the triangle. I'd have to know the radius of the circle. And we could use trigonometry in order to do that. But in general, what we need to know is as we divide these sides in half, the approximation gets closer and closer to the actual area of the circle. And then we could do the same thing on the outside. I could make an inscribed octagon or a circumscribed octagon, which would be a little more than the area of the circle. Okay, so I showed you with Geometry Sketchpad how we can make the polygon get more and more sides. It gets closer and closer to the area of the circle. Whether we do an inscribed polygon or a circumscribed polygon, the more sides we get, the closer it gets to the area of the circle. Now let's see where this formula actually comes from. Area equals pi r squared. So what we're going to do is we're going to take this circle right here and I'm going to divide it into 4 sectors. So to do that, I'm just going to fold the circle in half, and I'm going to fold it in half again. So I'm going to fold it over in half, like this. I'm going to fold it over in half again. And so now I have 4 equal sectors. And then I'm going to cut out those sectors. So I've cut out my sectors, and now I'm just going to arrange them so that they're alternating, like this. And right there, you can see that's kind of sort of a parallelogram, maybe, but there's a lot of space missing. So what we're now going to do, I'm going to take each one of these sectors, and I'm going to fold them in half. And I'm then going to cut them so that now I have 8 pieces. And then I'm going to rearrange them again. So now I took my 4 sectors and I cut them into 8 sectors. And you can see that it's getting a little closer to a rectangle. And now I'm going to do it one more time. I'm going to take each one and I'm going to fold them over so that I will have 16 sectors. Okay, so now I've cut those 8 sectors into 16 sectors, and as you can see, it's getting closer and closer to the shape of a rectangle. Now, if I could cut these infinitely many times, I would actually get a rectangle. And this length right here is half of the circle, so it is half of the circumference. And then this width of the rectangle is the radius, that is part of the sector there, so that's r. And then we can derive the area of the circle. The area of the circle would be 1/2 times the circumference. Well, some circumference is 2 times pi times the radius times the radius. So this right here is the length of our rectangle, and then this is our width of the rectangle. So area is length times width. And so half of 2 is 1. So the area of our rectangle, or our circle, is going to equal pi times r, which is r squared. So the area of a circle This is derived by cutting the circle infinitely many times with the length of 1/2 times the circumference times the width, which is the radius. So here's an example of where this might be applied. Which polygon inscribed in a circle has an area closest to pi square feet? Well, in order to estimate the area of the polygon that's inscribed, we can use the area of the circle to estimate it. So the area of a circle is 1/2 pi r squared, and the radius is 1/2. So this is 1/2 times pi times 1/2 squared. 1/2 squared is 1/4. 1/4 times 1/2 is 1/8 pi. Alright, this has the same area. The area of the circle equals 1/8 pi, but this one has a closer estimate to this because the polygon is 1, 2, 3, 4, 5, 6, 7, 8 sides, an octagon where this was a hexagon. Now this circle, if I find the area of the circle, area equals pi times radius squared. Our radius is 1, so that's pi times 1 squared, which is pi. So the area of the circle is pi. The hexagon is close to that area. Well, this circle has the same radius, but we have, again, an octagon instead of a hexagon. So because this octagon, there's less space in here, it is closer to the area of the circle than the hexagon is. So the correct answer, which one has the area closest to pi square feet, would be answer choice D.